Welcome back to compiler construction. We'll continue our discussion on parsing. So in the last two lectures we took a look at first top-down parsing, so building recursive decent parsers and then having this automated using a parsing table. And in the previous lecture we looked at the basics of bottom-up parsing, and we've seen a number of problems showing up with this. So today we are going to take a closer look at a refined version of bottom-up parsing, so-called LR parsing, which tries to get away from some of the problems we've seen before. So this is the overview of today's lecture. First, we're going to quickly revisit what we've learned about bottom-up parsing in the previous lecture. Then we'll talk about our major question or problem that showed up last time, so deciding when to shift and when to reduce. And then we'll introduce LR parsers, first a general idea, then a very important subclass of LR parsers, the so-called LR1 parsers, and we'll talk about different subclasses of parsers afterwards. So, top-down parsing, as we've already seen, it means we start with our grammar and we start with our start symbol, which we call sigma here, and then using our grammar rules we try to match the initial part of the input token stream to what rules are appropriate in our grammar here. So essentially at some state in your parsing, so when you've parsed part of your input, you have already derived a part of your syntax tree, and then you're currently at a non-terminal symbol that you're trying to derive. So what you're doing is you're trying to derive a partial syntax tree here, so just a subset of or part of the overall syntax tree from this non-terminal symbol alpha, and this actually matches a part of your input, which we call a V, and the start of this input is V1. That helps us to decide, well, which of the possibly different rules for a non-terminal symbol we are going to take while parsing our input. So at the point we're describing here, the parser tries to find a derivation for this alpha here. So if we have an input UU alpha U2, we want to modify it so essentially that we figure out that an input string or a partial input string V matches our non-terminal symbol alpha here. So we know that then the rest that remains here, UR, has to be derivable from U2 to complete parsing. If this doesn't work out because there's no rule to derive this remaining input, then we'll get a syntax error here. So this was top-down parsing, and we've seen ways to implement top-down parsing, and then we took a look at the other way around. So bottom-up parsing actually starts from your input token stream, and it tries to create the whole syntax tree from the bottom up, as the name says. So essentially, whenever there's an input token stream, we try to figure out, is there actually a rule that can produce this input token stream? And if so, we can reduce this part of the input token stream to this rule. So we reduce a set or a sequence of terminal symbols to a sequence consisting of a mix of terminal and non-terminal symbols. And for a partial input, we try to guess a production that actually generates our partial input here from a non-terminal symbol. So what we have to do is we have to read the rules from right to left in order to reduce a input sequence of non-terminal characters to a non-terminal symbol. So if we compare them, top-down and bottom-up parsing and the related syntax tree construction, top-down parsing, or LL1, decides to build a part of your syntax tree, a node of your syntax tree called X, after seeing the first token of its subtree here, and then it tries to decide, can we actually find some rule that generates a sequence starting with this token, whereas bottom-up parsing does it the other way around. So it first reads a subset or a subsequence of your input token string, and then it decides to build something higher up, like maybe it can reduce something to a non-terminal symbol B and something else to C. And ultimately, when it arrived at BC, it can figure out recursively that BC, this sequence here, could be reduced to a non-terminal symbol X, which then is at the root of our partial syntax tree. And then we build bigger and bigger partial syntax trees, combine them to eventually arrive at the complete syntax tree. So bottom-up parsing creates these partial subtrees, and we also call these partial subtrees for different parts of our input string just a forest. So here we have a slide demonstrating the general idea of bottom-up parsing. Again, you may remember this from our previous lecture. So as we said, bottom-up parsing starts from the input token stream. So we read a number of terminal symbols from our input token stream, and then we try to match them to some right-hand side of a production in our grammar. So when we did this matching, we can assume that this input token sequence can then be reduced to the non-terminal symbol that's printed on the left-hand side of our production here. So we reduce a string to the start symbol, and we do this by inverting the productions of our grammar. So essentially, in top-down parsing, we looked at our grammar in the following way. We looked at non-terminal symbols on the left-hand side and then figured out what needs to be on the right-hand side of this production for this, to take this production here for E and T, for example. And when we do bottom-up parsing, we simply reverse the direction, so we know if there's something that starts with int and a multiplication symbol and then something like a t behind it, then we can reduce this here to just a non-terminal symbol t. So let's consider the input token stream, which is just int times int plus int. And we've seen that to resolve this and to figure out our bottom-up parsing, so to arrive at our start symbol, we need to read productions from right to left. So we started just reading part of the input string here, int times int. And we figured out, okay, this int can be reduced to a t, so we replace this int by a t here. Then we find a sequence int times t, which we know can be reduced to a simple t. And then we have t plus int, so the only thing matching the int at the end is this rule here, going from int to t. So we replace the int by a t. Then we have a sequence t plus t. The only thing matching a t at the end is this rule up here, so we reduce this t to an e. We arrive at t plus e, and this is now the first production for e. So finally, we have reduced our input token sequence to a simple start symbol e, so we know when we read these productions in reverse, matched the right ones, and arrived at the start symbol, that the string we input here to our grammar, to our parser, is actually a valid string in our language here. Now, one problem we've seen already the last time is when we started looking at that sequence here, we could have already chosen to use a production at the first int we read, because that rule here, int to t, would have matched. So the big question is, why didn't we actually immediately reduce this first int here in the token stream using this production? And this is what we're going to take a closer look at in the following slides. So, to take the right decision, so whether to require an additional symbol, to read an additional symbol, or trying to reduce what has already been read, so what's on your internal input stack, we extend our bottom-up parser by, well, a tiny bit, and this is called LR parsing. So the first thing we need to do to enable a well-formed LR parser is we extend our grammar by adding a special token EOF, which stands for end of file, and we usually symbolize this by the dollar character. So this gives us an indication when the input stream is actually finished. And we also add an extra start rule. The extra start rule is just a bit of syntactic sugar, but it makes it easier for us to determine when we have arrived at the start rule, because the start rule only is one rule leading to something else and the end of input string. So this is uniquely identifiable. So as before, our parser uses a stack of terminal and non-terminal symbols, and our parser looks at the current input token and then decides between one of the following actions. So we've seen two of these actions before. One action is shift, so our parser decides, it pushes the input token onto the stack and reads the next token because maybe it couldn't resolve something or it decided to first go on and shift before resolving something. Then reduce. So reducing actually takes a part of the input token sequence that's already read, so that has been pushed on the stack, and this is matched with some of the right-hand side of a production. So essentially we take all of the right-hand sides of our productions here and try to match the top of our stack to these productions here. So when we do this reduction, we pop all these symbols from the stack and then push instead the left-hand side of that production, so the non-terminal symbol that's on the left-hand side of the matching production on the stack. And at the same time, we can then build the part of our source tree, of our parse tree, in order to do it step by step while we're just reading the input string. And we have an additional action, and this action is called accept. So when the parser recognizes it's about to shift the end of our input, the dollar, our parse is complete. And the parser can use a DFA, which we can encode in a table, to actually decide which action to take and to which state it should go after each of the shift actions. So let's take a look at an example for LR parsing. We have this grammar here on the top right. So you see we've introduced a special start symbol S, which only resolves to some additional symbol S TMT, which stands for statement, and the end of the input string. So, well, there is a statement, and after the statement, our input has to end. So our statement is just an assignment statement, so this resolves to some identifier, an equals sign, so to terminal symbols, and then a non-terminal symbol exp for expression. And an expression is very simple, so an expression can either be a simple identifier, or an expression can be yet another expression, a plus terminal symbol, and another ID terminal symbol. So here you see we didn't use the OR sign to write the second production, but we used a separate production from exp non-terminal symbol to something else. But that has exactly the same meaning as if we just wrote exp to it or exp plus it. So our notation is the same as before. So we have our stack that we have read or constructed so far. Then we have this red arrow indicating the current position in our input stream. And we have the rest of the input on the right-hand side. So when we start parsing this input string, ID equals ID plus ID and the end of the input, of course we start before the first input token. So the first thing we need to do is to get one of the input tokens. So we shift by one position here, and well, the next thing we do is we shift by another position, and then we shift once again, so our input pointer is after the second ID in our input token string. Then we reduce the input read so far, ID equals ID. So what can we reduce here? Now there is no rule saying ID equals ID immediately here, so the first thing we need to reduce is the second ID, and we can reduce the second ID using rule number 2 here. So by reading it from right to left, we reduce ID to an exp. So essentially we replace this ID here by its non-terminal symbol x, which was on the left-hand side of its production here. So we end up at ID equals exp. And now at the same time, we build our syntax tree. So we know that we derived ID from exp, so we build our partial syntax tree here, a very small one obviously, which just has the terminal symbol ID at its leaf of this very small syntax tree and an inner node exp. So we're still at this point of the input stream because reduction doesn't move our input pointer, so we can continue up here. So now we can decide to shift again. So when we shift, we read ID equals exp plus. We have this part of the syntax tree again, of course, we don't throw it away. And we shift once more, so we have ID equals exp plus ID. Now We can try to find another rule, and we see rule number 3 is the one that works here. So exp to exp plus id, read from right to left, means we replace this part of our stack simply by exp and add this information to our syntax tree. So exp plus id is replaced by exp, and we add the resolution of exp to exp plus id, and then the partial tree we've built before to our partial syntax tree we have built. And then we have id equals exp, and this is rule number 1. So we can apply rule number 1 from right to left by replacing this id equals exp simply by statement, adding this information that statement derives id equals exp, and the rest we've built before below. And then we finish parsing. So the next input character here is our dollar character. So when we shift this, we know that our input has ended. So we have arrived at our S rule. We haven't put this here due to space concerns, but of course, you know, when you are at statement, the only thing we can go to is S again and the end of the input. And so we've successfully parsed our input string here, so we know it's a valid word in our language. So in order to build this machine that helps us determining whether to shift or to reduce in a certain state of the input stream, the parser uses a DFA, and in this DFA we have certain states, and these states are sets of what we call LR items. So an LR item is essentially an extended production. So a production would be non-terminal symbol X is derived to some mix of terminal non-terminal symbols alpha and beta. And we extend this by two things. The first thing is this dot you see here in the middle. So this dot indicates the position in the input sequence we're currently at. So we've already read some part alpha, and we're going to read some part beta. And the second addition is on the right hand side here, and this gives one or more possible look-ahead terminal symbols. So in this case, two terminal symbols T and S. If the lookahead doesn't matter, we actually just use a question mark here, because it can be arbitrary here. So this LR1 item corresponds to a certain state in our DFA, where the topmost part of our stack is alpha, and remember, alpha is a combination, a sequence of terminal and non-terminal symbols, and the first part of the remaining input is expected to match beta, followed by either a T or an S as terminal symbol. So it's not only the beta that matters, but we need T or S after the beta in addition. So how do we construct our DFA? Let's start by constructing the first state of our DFA. So we should obviously start at the start of our grammar. So what we do is we take our start production, and well, we need to model something that corresponds to the start of our parsing. So we place our dot indicating the current position in our input stream just at the beginning of our production here on the right hand side, because actually at the start we haven't read anything. So at the start we know we can, if we're here, derive an E like a non-terminal symbol, and then our input is ended, and that doesn't depend on anything coming afterwards here. So now we see that there is a non-terminal symbol E right after our dot here, and this is followed by a terminal dollar. So what we now have to do is we have to dig down in our grammar to all these sequences here. So essentially to all sequences which have an E as a non-terminal symbol on the left-hand side. And then we know whenever this E shows up that is derived directly from S, a dollar is the next thing that has to follow. So what we do is we add the productions for E to our state with our dollar as the look-ahead, so the end of the input. So we take production number 1 and 2 in our grammar here and add them. So here we're still at the start, obviously, because we haven't consumed any token yet, and we know adding these productions here then means after these productions we need to have the end of the input or something's wrong. And then we see that there's an additional non-terminal symbol t now, right after the dot, after we added the productions for e. And this can be followed either by a plus sign and something else, or it's immediately followed by the end of input. So now what we have to do is add all the productions for t with a plus and a dollar at the, as a lookahead. Now we only have one production for t, which goes to ID. So what we can do here is we can use this shorthand form by writing the symbols that are expected to follow the ID just on the same line, separated by a comma. So we add this one rule here, and we know that if we take a look at this rule here, then the next symbol has to be either a plus or the end of the input. So now we have added productions for all non-terminal symbols that are right after the dot, because we don't have any more non-terminal symbols actually, so nothing more can be added. So we have finished with constructing our first state. So what we've done here, adding these new productions for non-terminals following the dot until we can add no more productions because we ran out of non-terminal symbols. This is called taking the closure of the LR item set. And now we can go on constructing the next states. So from this state 1, we've already seen here, we need to consider, well, what else can follow here. So essentially, the next thing we have to do is, when going from one state to a different one, we have to consume one input token here. So essentially, from state 1, we can consume the first token of the first production here, so S2 dot E dollar, and we move our input token one position forward. So our state 2 consists of S goes to E input token position end of input. Again, this is not dependent on any subsequent input character. Then we can do the same if we read a T as the first symbol here. So if we read a T, we can go from E to this production here or to that production here. So we add both of them to state 3 here. So in state 3, we add just these productions with a dollar at the end. And finally, we have our last production here, T to it, which means we read a terminal symbol ID or it, and then we add this rule here as state 4. So note that the dot is followed by E, T, or ID in state 1. So for each of these symbols, which we can read as a subsequent symbol, we create a new set of LR items, and we advance the dot past that symbol that's been read, and then we complete the states by taking the closure. Note in this case, nothing had to be added for this set of states, which we just introduced. So now we can continue adding the remaining states. So in state 3, we have the situation that for the first rule in state 3, we could read a plus sign. So the next thing in our parse sequence would be that plus. And after that plus, we have an E. So essentially, we would have to add all the rules here and take the closure here. So we have E to T plus and then an E, and then we take the closure of the rest of the symbols like we've done here on the left hand side, and then we can continue by finding yet something else. So we can find that we've successfully read the whole input token stream here, so we add another state here with a dollar at the end, or if we read an ID, well, we go to state 4 again. So you see what we do is we reuse states. So if two different states, so a new state that we have generate and an existing state, have exactly the same set of rules and the same set of following characters in the same position of the dot, then we just reuse it by adding an arrow into our DFA transition graph here. So we complete the DFA by advancing the dot, creating the appropriate new states, and complete them by taking the closure. And if there's already a state that has exactly the same DFA LR items, then we just reuse that state to make our graph a bit more simple. Now, when constructing scanners, we've already seen that there is a correspondence between a DFA and a table that expresses the DFA states and transitions here. So we can do the same now for our parser. If we want to write or generate a parser, we express this DFA we've just constructed using a table. So for each token edge t, we've just added to our graph from a state j to a state k. This means that we're consuming this token t. So we have several tokens here, and then we add a shift action, which is just S for shift, and then a K for a go to some certain subsequent state K to our table at the position, well, that indicates this current state here and a current token here, so the position JT in our array here. So this is equivalent to reading a token and pushing it onto the stack for a bottom-up parser. So for each state j that contains an LR item where the dot is at the end, we can then reduce this because we've read all the input tokens that are part of our production here. So we're at the end of this production. We've successfully read this, so we can reduce this. So if this is the state, then we can add a reduce action, which we call R, and then we reduce to some P to this table at position JT, where P is the production, and then the T is the look-ahead token that's at the end of the rule. So this is the equivalent of popping the right-hand side of a production of the stack. And then for each non-terminal edge X, which goes from state J to state K, so there's a non-terminal, we just add a goto action, which we call G for goto, and then go to a state K, to a table at the position that indicates the number of the rule and some non-terminal symbol X, like the E and T in our case here. So this would be equivalent then to push the left-hand side non-terminal onto the stack. So you see, we've just split the actions that we take into the actions that we've described before, and we generate a separate entry for shift, reduce, so just removing step from the input stack and then replacing it by this goto action by some new non-terminal symbol. So that's our stack modification in these two steps here, and this up here is our shift action. Now we've seen the additional action we wanted to add is the accept action. So for a state J that contains an LR item with a dot to the left of the dollar, we add an accept action, which is just A to our table, which has the special input symbol dollar here. So essentially it would be somewhere here, and this would indicate our parser can finish and is completed because it has successfully parsed all the input string if we're about to shift dollar. So this is the LR table for our simple example. So for example, in state 1, when we read an identifier, we shift and go to state 4. In state 4, when we read a plus sign, we can reduce and go to production 3. So this is not state 3, but we use production 3 here. Or in state 3, when we read a dollar symbol, we can reduce to P2, production 2. And for the non-terminal symbols that we read, for example, in state 1, if we have an E, we go to production 2. And otherwise, we go to action 2, and otherwise we go to action 3. So a good example or a good exercise for you would just be to try to reproduce the table here that we've just shown from the graph on the previous slides. Of course, we've done it here for you in a bit, so we can see whatever happens here when we're in state 1. For example, let's just take a look at the right-hand side here. We read an E, we go to state 2. When we're in state 1, we read a T, we go to state 3. And finally, when we're in state 1 and we read a terminal symbol, which is ID, then what we do is we do a shift. So we move our pointer here one further to the right. So we've read an ID here, and we shift it, and we're finally in state 4. So in state 4, for example, we're at the end of our input string. So two things can happen. One thing that can happen is we read a dollar sign. So in state 4 and we read a dollar sign, we use P3, this reduction here. Or, well, if we read a plus sign, then we can also reduce this using P3, just going from it back to T and build a parse of our syntax tree. So all of this is not very complicated, but it involves just a bit of understanding of the parsing process, so it's probably very helpful that you try to reconstruct this table on your own, going from our DFA graph here to our table. And so the next question that remains is, how do we actually implement a parser based on this table?